Namaste and welcome back to the course on statistical mechanics of phases and phase transitions. We are discussing the Ising model. So let's briefly recap what we have done so far. So we discussed at length the Ising model in one spatial dimension on a chain actually. And what we discovered is that there is no finite temperature phase transition. You just have a broken symmetry state at 0 temperature, but in the thermodynamic limit at any temperature finite, the symmetry is restored back and you do not have any magnetic order. So this restoration of symmetry takes place because of domain wall excitations, which become spontaneous because of the entropy gain. And a very important new idea that emerged from our discussions was that in the Ising model, even though there is no order at finite temperature, we do see that there is an emergent length scale, and this is called the correlation length. The correlation length goes to 0 as temperature goes to infinity, but it grows unboundedly as you approach the 0 temperature. So this is the essential physics of the Ising model in one dimension. And in the process of discovering this physical results, we also learned some techniques. Namely, we learned that we can do some transformations to linked variables, and that helped us solve the problem. And we learned a more important and perhaps a more general concept called as the transfer matrix idea. And we use transfer matrix actually to solve the one-dimensional Ising model and obtain variety of results. So the natural next step is to go 2 dimensions. So what we will try to do is we will try to start discussing the Ising model in 2 dimensions in this lecture. And the main point I would like to emphasize in this lecture is more like physical understanding of the excitations and what they do to the magnetic order and stuff like that. And in particular, we will be visiting the idea of Peierls, who provided a very nice argument quite a while back, almost 100 years back, on trying to understand the low temperature phase of the Ising model. Okay, so let's get our language set up properly so that we can use it in the discussion that follows. So what I'm going to do is I'm going to start with a square lattice Ising model. So that's the square lattice. And let me say that I have L tilde sites this way and L tilde sites the other way, so that the total number of sites is L tilde square. And each site I'm going to label by this capital I, and I'm going to use periodic boundary conditions. So it's a very simple setting, something that we are quite familiar with. The configuration of spins which I place at each of this site is given by the set of all SIs. SI is the spin associated with the site I. And each of them can take plus or minus 1 values or up or down values, and this will lead to 2 to the power n configurations possible. And the Hamiltonian, of course, is our ferromagnetic Ising model with an exchange coupling J, and we just have nearest neighbor interactions, so it's the simplest possible setting. Okay, several lectures back we discussed how you find the ground state of this model by using a symmetry breaking field, applying a symmetry breaking field, running to the thermodynamic limit, and then taking the symmetry breaking field to 0. And if you do it in a certain way, that is, the applied symmetry breaking field is in the positive sense, then you will end up with this ferromagnetic ground state. And as we know, this ferromagnetic ground state breaks the Z2 symmetry. So the question now is, what happens if I go to finite temperatures? So one dimension was a little anticlimactic in the sense that when we went to any finite temperature, this spontaneously broken symmetry just vanished and you just got a paramagnet. What is the story in 2 dimensions? Does this broken symmetry survive, or is it again destroyed by certain excitations? So this is what we will explore in this lecture. So to do this, just as we did in one dimension, we have to explore what are the excited states of the system. Okay, so the first excited state can be realized by flipping spin at some particular site. You can choose whichever site you want to flip this at. So you can flip this if you flip the spin, then I will say that 4 links, you see these 4 links, these were indicated by red, their energies will go up by 2j, because originally each of these links provided an energy of minus j because both the spins were up. Now one spin is up and the other spin is down on this link, for example, and therefore the energy is increased to plus j, therefore the increase of energy is plus 2j. So that's the energy increase. So if I flip a spin, I'm going to sort of frustrate 4 links. 4 links are going, each of them are going to go 2j above, and this is going to cost me an energy of 8j. Okay. So this is of course a gapped excitation. You can take the thermodynamic limit and you will see that the energy will remain at 8j, and this is okay. Now the question is, if I just assume for a moment that these are the only type of excitations that are allowed, can I populate in the system at a finite temperature a finite number or some finite concentration, I should say, of single spin flips at different sites? So they may be very dilute, or they may proliferate, we don't know, but we want to estimate whether single spin flips can actually destroy the order, or what does it do to the magnetic order, to the magnetization. Remember, the magnetization that we found in the way we applied the symmetry breaking field and found the ground state, the magnetization at 0 temperature was unity, that every site was polarized up, so the polarization per site is 1. So the question we want to ask is, if I increase temperature, can I proliferate, or can I have a set of excitations that are, let's say, just the single spin flips that can possibly destroy the magnetic order? Okay. So this is the question we would like to explore. So let's try to see what is the effect of single spin flips. So what we will try to do is, we will try to estimate how much magnetization is reduced by using free energy arguments, pretty much the same arguments extended to 2 dimensions that we performed in the 1-dimensional case when we studied domain wall excitations. Okay. So what I am going to assume now is that, let's say that I have n sites in the sample, in my system, sorry, and let's say that I have a state where n down sites have down spins. Okay. This means in such a state where there are n down sites with down spins, the concentration of downspin sites, little n down, is this capital N down by n. Okay. So now what I would like to do is, I want to ask, if I have n down spins, capital N down spins on a lattice with n sites, what is the entropy I can gain by sort of arranging them in different ways on the lattice? Okay. So this is an important calculation. I will indicate the steps as we go along. So how can I place n down spins on a lattice with n sites? Of course, the other sites, n minus n down spins, have up spins. So this is a simple combinatorics problem. So you will realize that the answer is just n choose n down. So I just choose n down sites, and there is the number of ways of choosing the n down sites. So that's the number of ways, what I am indicating inside the parenthesis, that's the number of ways I can put n down spins on a lattice with n sites. So that is n factorial by n minus n down factorial times n down factorial. Okay. So we are going to assume that all the numbers as here are large, and I am going to use the Stirling approximation, and the Stirling approximation says that n log of n factorial can be thought of approximately as n log n minus n. So that's the Stirling approximation. So this is the log of the numerator, log of n factorial, so that's n log n minus n, and then I have the approximation for n minus n down factorial, that is what I have written here. And similarly another term for n log of n factorial, n down factorial, and that is what I have written here. Okay. Now if you work through the algebra a little bit, you will find that this goes as this, what I have shown here. And if you do further use this definition of little n down, which is the concentration of the down spins, then you will see that the entropy goes like this: minus n number of sites, open bracket, 1 minus concentration of down spins log 1 minus concentration of down spins plus concentration of down spins log concentration of down spins. Okay. Now, this kind of expression for entropy is a very important result. You will see this in many different contexts. So, for example, if you want to see vacancy formation in solids, there are many different contexts in which this kind of expression for the entropy will show up. So, broadly this is called entropy of mixing. So, it's good to be familiar with this. Okay. So, we have estimated the entropy. Okay. Now, what I am going to do is I am going to find out what is the change in the free energy if I have n down number of spins. If I have n down number of down spins, then they will cost me an energy 8j times n down. So, in making this statement, I am assuming that the spin flips are not on neighboring sites. So, this is like already assuming that there is a dilute concentration of this. Okay. So, we are assuming that the spin flip states are well separated. We will check whether that works out correctly. So, that is the energy part, that is the excitation energy of having n down spins, n down spins, minus temperature, whatever temperature you are working at, times the entropy associated with having this. Okay. Now, I can compute from this whole story, I can compute the free energy change per site, right. So, this is something like a free energy change, density of free energy change, delta little f. Yeah, we are familiar with this from the previous lecture also. And this turns out to be 8j times the concentration of down spins plus T times this entropy of mixing as a function of the concentration of down spins. So, this is the change in the free energy of the system if I have a concentration of little n down spins. So, what is the equilibrium concentration? The equilibrium concentration of down spins will be the one that minimizes the free energy. So, this is a very straightforward calculation. You can do this, and I have just indicated how this is done. So, we have this term here, this change of free energy. So, you just minimize this with respect to n down, and then you will find that the equilibrium concentration n down is obtained in this following fashion. So, you will see that the equilibrium concentration of down spins is exponential minus 8j by T. So, it is something like an activated kind of term, right. It looks something like thermal activation kind of phenomena. So, this is not unexpected, and what you find is something very interesting. Magnetization of a function as a function of temperature is 1 minus the concentration of down spins, equilibrium concentration of down spins, and that is 1 minus e to the minus 8j by T. So, this is very nice. It tells you that single spin flips cannot destroy the magnetization. So, what is the difference between one dimension and here is that in one dimension single spin flips gained you a lot of entropy. Here there is an entropy gain, but that entropy gain is not sufficient to overcome the energy that you have to pay for having all these down spins. So, this is very encouraging. This is very encouraging because we at least see that some very simple excitations cannot destroy our magnetic order at 0 temperatures, that survives. But you may not be very happy with this because the point I was making is that spontaneous magnetism is not destroyed by single spin flip excitations. So, you may wonder, what if I flip spins on some larger domains? So, for example, you might say, oh, I could have excitations such as this. So, lots of spins are flipped. So, you see the magnetization will reduce because if such excitations are possible and if they become spontaneous, then of course you are going to reduce magnetization. Okay. So, this is what we call as a domain kind of excitation, and this magenta line here is the domain wall. In fact, if you pause for a moment and think about it, you will realize that the single spin flip is the smallest possible domain. right? So that's the domain wall perimeter that I'm showing here. So question is, what is the energy of such an excitation? We know the energy of this excitation is 8J. So if you think about this, you will instantly realize that the energy of the domain is actually proportional to its perimeter, that is the length of the domain wall. Now let's see what that means. So you see, this magenta line can be thought of as the domain wall, and the length of the domain wall, if you just think for a moment, is proportional to the number of links that are present on the domain wall. So for example, that is become a red link: 1, 2, 3, 4, 5, 6, 7, 8, and so on. And you can just count this, and you see that is the length of the domain wall. This set of the number of links that have been cut. That is the cut meaning excited, the ones that are indicated by red, right? So if I call the domain length of the domain wall is little l. So for example, here there are 14 red lines here, and therefore the energy of a single split is proportional to L equal to 14. And for a single spin flip, for this one, L is 4. You see, that's 1, 2, 3, 4. So the length of the smallest, the perimeter of the smallest domain is 4, and then it can take any even value. If you think about it, if I have a closed domain wall, you have to have even, the length of the domain wall has to be even. So what is the energy of the domain wall? So you know that the length of the domain wall is proportional to the number of links that have been excited. So if L is the length of the domain wall, it will be 2L times J, because every link that is excited will give you 2J of energy. So this is quite interesting. So the energy of a domain, excitation energy of a domain, grows proportional to its perimeter, and it grows linearly in the perimeter, right? Now this poses an interesting question. Can such domain walls kill the magnetization at finite temperature? So we are asking a slightly different question. If you only allowed this, then we were not destroying magnetization. Now we are also going to allow these things. So what is required now is to estimate the number of ways these can occur, namely you have to estimate the entropy and so on. So this was a very interesting problem, and it was answered roughly 100 years back, right? And this was I think 90 years back roughly, right? This argument was given by Rudolf Peierls, who is a very well-known theoretical physicist. So Peierls made the following argument, right? He claimed that these domain excitations cannot destroy the magnetic order at 0 temperature. That the magnetic order present at 0 temperature, when you come to finite temperature, cannot be destroyed by such domain excitations. What I am going to show you is not the full detailed sort of modern version of Peierls' argument, and I would encourage you to look at this paper by Griffiths. I will give you a more crude but physically sound, I guess, argument. Okay. So to do this, I look at the lattice and I want to find out how many different ways I can make domains of a given length. So how do I think about a domain? For this, I need to introduce a concept, namely the concept of a dual lattice. So what is this picture here? The picture is telling you these blue sides here are the sides of my lattice. And if you take the placket, namely the square of the lattice, and look at the centers of these, you see they also form some regular arrangement of sides in space. So you can construct a lattice out of this. So this is called as the dual lattice. So I start with the dual lattice and I realize something. I realize that domains can be formed by walking on the dual lattice. So let me explain what I mean by that. So this is a dual lattice site. So I am starting here and I am going to walk. So I go to the next site, next site, next site, next site. When I reach here, I turn left and then I go this way. I turn left again. I do this. I come back here. and that encloses something in my original lattice. So I'm walking in the dual lattice, and that encloses a region in my original lattice. What is the region? So you take all the sides, and as I'm walking around this, I'm cutting these links. You see that will form the perimeter. Number of links of my original lattice that are cut, that will form the perimeter, and all the sides inside form the region of the domain. And what I have to do is, the rule is, after I perform this walk, I simply flip all the spins inside. So this is very interesting. So I have found a way to make domains by walking on the lattice and just finding the area enclosed by the loop that I am performing on the lattice and just flipping all the spins inside. So how can I estimate the entropy now? The entropy can be estimated by simply counting the number of ways I can perform walks in the lattice of a given length. So you see here, the number of steps that I took is actually proportional to the perimeter. It's proportional to the number of links of my original lattice that I'm cutting in the walk. Okay, so this is the idea, right? So the key idea is that we use domain walls, we visualize domain walls as walks in the dual lattice, right? A closed path on the dual lattice will enclose a domain, and all spins at domain are flipped. Okay, all right. Now comes an interesting observation. Suppose the perimeter of the domain wall that is formed, or the length of the walk, is little l. Then for sure the area enclosed here is less than or equal to L square by 16. How do we see this? So this is an elementary exercise. If I were to take some polygon with a total perimeter L, you can show that the one that encloses the maximum area is the square, and that is what. So we just say that if I have a perimeter of my walk equal to L, then the maximum possible area that it can enclose, that the area is proportional to the number of downspins that are going to be flipped, in number of spins that are going to be flipped, namely the number of downspins in the domain. That will be proportional to, that will be certainly less than or equal to L square by 16. Okay, so it's an upper bound for the number of downspins that are present in the domain. Okay. So now we'll go through the Peierls argument. Peierls argument now is to estimate what is the average number of downspin sites in the system if I am allowing all these different types of walks. Namely, I am allowing all these different types of domains to form. Okay, so how do I do that? First is, we have to estimate, if I give you the wall length L, how many domains can I form? Okay, how many different ways are there to form domains of wall length L? Okay, how do I do that? So I know that I'm going to do walks on the lattice. So to walk on the lattice, I have to start somewhere. How many ways are there to start? Well, I can pick any site of the dual lattice. So there are n ways to start. So there are n sites on the dual lattice where I can start. So I can start in n ways. Okay. Now the first, I started n ways, and the first step I am going to take, I can take in any direction. So I take in any direction, and I will never traverse my walk back. I'm just going to go. After that, I'll go. So when I start here, I can go to the east, north, west, or south. So the first one has 4 ways. After, let's say I took the first step here. Now you see, I have 3 ways. I can choose either north or south or whichever one. So if I've done some steps, at any step after that, I have 3 choices. I can go left, right, or I can go up, down, or if I want to think of directions, I can go east, north, south, whichever way I can, but there will be 3 ways. So now you will see, strictly I should impose the condition that the domain wall, the walk closes back and that it comes back to where it started. But I am not going to bother about any such thing, because I want a bound. I want the maximum number of possible domains of length L, right? Perimeter, the wall length L. So now I just say that I don't even bother to check whether these are going to close on themselves. So I see that omega L is less than or equal to the number of sites times 4, this is the number of ways I can step the first one, times 3 power L minus 1. Okay. Why is 3 power L minus 1? For I have to take L steps every time after the first one. I have 3 choices. So I have to take L minus 1 steps with 3 choices, and that's why it's 3 to the L minus 1. So this gives me an upper bound for omega of L. Okay. So what is the probability of realizing a domain wall of length L? So that is a more detailed and difficult calculation, but we can certainly put a bound on it. What is the bound? So you just assume that there is a domain whose wall length is L. We know that the energy associated with that is 2 little l, the length of the wall, times J. J is the exchange constant. So the thermal excitation probability of such such a domain wall excitations will certainly be less than or equal to e to the minus beta times 2L times J. This is for sure. It cannot exceed this. So we have got a bound on the probability. Okay. So now what we can do is, taking all of this information together, we can estimate what is the average number of downspins in the system that are on an average excited when all such domain wall excitations are allowed. So how do I do this calculation? All right, I'll just walk you through this. So the average number of downspins is sum over all possible domain walls, the number of downspins associated with the domain of wall of length L, times the number of ways such domain walls of length L can be realized, times the probability associated with exciting a domain of wall length L. So this is a fairly general formula. Now we have estimated all these numbers and we have got upper bounds for all of those numbers. So this quantity will be less than or equal to, because every one of the terms we have done here are upper bounds. So the number of spins that are going to be flipped when the wall length is L is less than or equal to L square by 16. Omega L, the number of different domains, different configurations of domain walls domain excitations you can get when the wall length is L, is bounded by 4n times 3 to L minus 1, and that is the probability e to the minus beta, beta is 1 by temperature, recall, times 2L times J. J is the exchange constant. Okay, so now the rest is algebra. So you can just massage this into some set of expressions and you can actually find that n down, average number of spins, is proportional to n times some number. It's a fairly big number, let's say. It's not order 1, that's what I mean, right? And multiplied by a to the minus 8j by t. But friends, you must recall that this is exactly the exponent that we found with single domain wall, single spin flip excitations. So if you put all these things together, when temperature is much less than J, m of t is 1 minus average number of n down by n. So that's like the average concentration of downspins now is equal to 1 times 2 square 3 to the 5 8 to the minus j by t. So now you see this is dying exponentially. So if I go temperature much smaller than J, this can be made as small as I want, and therefore the magnetization will be only very slightly lower than 1 if I am at low enough temperatures, despite the fact that this is a fairly big number. This exponential will kill any finite big number, even however big, right? And what is most interesting to observe is that this is qualitatively same as the single spin excitations that we had a single spin flip excitations, and we got a number of 1. So all that this domain wall calculation, the domain excitation calculation did for us was to change this prefactor of this exponential by, it gave us something which is 2 orders of magnitude bigger, let's say. That's all that it did. Okay, so it's qualitatively the same result. And so what Peierls argued based on this is that the zero temperature broken symmetry state that survives to a small finite temperature T much smaller than J. You can even use this to estimate at what temperature this will go to 0. That's not a particularly revealing calculation in the sense that we have made too many estimates here, so it may not give a quantitatively correct result, but you will see that that will give you some estimate. So what have we learned now? What we have learned now is, so unlike the zero temperature, unlike the one dimensional case where the zero temperature broken symmetry state is just a state at 0 temperature and it's instantaneously destroyed if you increase the temperature by even a little amount in the thermodynamic limit. What you see is that there is a broken symmetry ferromagnetic phase at low enough temperatures. At finite temperature T greater than 0, there is a phase, there is a regime of temperature where you have ferromagnetism. So that's why we call it a ferromagnetic phase. Okay, so let me summarize what we have studied in this lecture. I will discuss Ising model in 1 and 2 dimensions. So Ising model in 1 dimension breaks symmetry at T equal to 0, but for any finite temperature it is a paramagnet. So that's what I have shown here. So when you go T to 0, there is a magnetization of 1, but for any finite temperature it goes to 0 and then you have no broken symmetry and you just a paramagnet. What happens in 2 dimensions is very interesting, very different as well. You have a broken symmetry state with magnetization 1 at 0 temperature, and what happens is when I increase temperature, the magnetization reduces by an exponentially small quantity e to the minus 8j by t. So you have a regime where the system is still in the broken symmetry state, and this regime is why we call it a phase. There is a regime of parameters where the symmetry is broken and therefore there is a broken symmetry phase here. And that phase is what we call as the ferromagnet. Okay, if you go very high temperatures, we have not made quantitative or estimate arguments for this, but it's quite sort of physically convincing that if you go to very high temperatures where T is say much greater than J, say T is let's say 10 or 20 J or something like that, then we'll certainly not have any broken symmetry state. We'll just have a paramagnet where each spin will be doing whatever thermal dance it wants to do, and therefore you will not be able to stabilize any kind of ferromagnet. So what happens here is the low temperature is a ferromagnet and the high temperature is a paramagnet with no broken symmetry. So a natural question to ask is, how does this change from the broken symmetry phase to this paramagnetic phase? Okay, it's also good at this point for us to revise or recall why the physics is so different in 1 and 2 dimensions. So in 1 dimension you got these domain wall excitations. They are gapped excitations, but they produce a lot of entropy. Having such domain wall excitations will gain a lot of entropy for you, and entropy gain is able to beat the energy cost, and therefore in the thermodynamic limit the domains win and they will destroy the magnetic order. In 2 dimensions, energy of the domain wall starts to grow, starts to depend on the size. Remember, in 1 dimension energy of the domains did not depend on the length of the domains. Here they start to depend on the size. So if I want to substantially reduce magnetization, I have to start producing big domains, but big domains, their energy costs are high, so they are less probable. And this physics that comes because the domain energy is proportional to the wall length, that does not allow entropy to gain an upper hand over energy. And this forces the ferromagnet to survive, or this makes the ferromagnet stable to these kind of domain fluctuations. Okay. So this is the physics behind why Ising model in 1 and 2 dimensions are so different, and is already a very illuminating result in that spatial dimension can play a very critical role in determining phases of matter. So that is a very insightful result that is coming out of this discussion. Okay, so we have now convinced ourselves that the Ising model in 2 dimensions has a broken symmetry phase and a paramagnetic phase, and we believe that there is some sort of phase transition. So our next stop is we would like to explore this phase transition, and in particular in the next lecture we are going to see an extremely important concept called as duality. And I am sure that given all these exciting results, you will join me for that next lecture. Thank you.